Hello, this module will be about some basic of probabilities. It's an important thing for data scientists. We will talk about experiments, outcomes and sample spaces. We will try to do conditional probability. Thanks to the conditional probability, you will try to create a spam filter, and then we will talk about sampling and confidence intervals. This is outlined for the other two lectures as well. Why is probability important? Well, random things occur in daily life all the time, right? So it's a good idea to try to make sense out of them a little bit. The probability can help us make sense of these uncertain things, right? But it will help us is to guide our judgments or actions based on what is likely to happen, or to know how likely things are to happen, right? In our case, for data science, we will try to see how often or likely things happen in the data, and then maybe based on that you can try to have some estimate of how things look like. So this is the basic language of probability. So experiment, it's something that is happening. So that's the thing that you try to do, some procedure, and the result of the experiment is outcome. There may be different outcomes for one experiment, and sample space is set of all possible outcomes. So for example, here is the easy one. If you roll a dice, that's an experiment. You are rolling the dice. Usually the experiment is that you are doing something. The outcome is what is the number on the dice on the top, right? So here, after the die stops rolling, you'll see 1. So that's an outcome. And sample space is all possible outcomes. You can have sample space 1, 2, 3, 4, 5, 6. So event is a subset of sample space. So if you do experiment, you have outcome, and if you look at several different outcomes together, that would be an event, right? So for example, you can have a simple event where event is exactly the same thing as outcome. For example, event, you are rolling 1, the same as the outcome that 1 was rolled. Another more complicated is that one event can have several different outcomes that make it happen. So here is example that your event would be you rolled an odd number. Okay? So the event is odd number was rolled, and the outcomes of the experiment that make the event happen is 1, 3, or 5. Right? So in other words, event is several possible outcomes together. Right? That you want to say that one of these happens, and that's the event. So here is a quick calculation. So assume that all outcomes are equally likely, right? So what's the chance of event happening? So you look at all the possible outcomes that make A happen, and you divide it by the number of total outcomes. So for example, in the dice, if you want to look at the event that 1 is being rolled, then there are 6 possible outcomes, and 1 is the size of the outcomes, how many outcomes make 1 on the dice. So the chance would be 1 over 6. If you would like to have the event of even number, then possible outcomes that make the even number happen are 2, 4, and 6. So there are 3. So the number of outcomes that make A happen would be 3, and total number of outcomes is 6. So 3/6, which is 1/2 or 50%. Right, here are few basic features about the probability. The lowest value of probability is 0. It is for events that don't happen. So chance of the event is impossible. For example, if you have dice and you say, I would like to have a number that is both odd and even. So this event is empty. There is no outcome that will make it satisfied. So impossible event. Highest value of probability is 1. It's the chance of event is certain. For example, you can have event that is the dice will show odd or even number. If you have odd or even number, then all 6 possible outcomes are valid for this event, and there are 6 total outcomes, so 6/6, which is 1 or 100%. And last property, that if an event have 70% chance that it does not happen, it have a 70% chance, then the chance it does not happen is 100% minus 70%. Right? So the chance of event happening and not happening must sum to 100%. Or you can have it in the 0 to 1 range. So if you have a chance of event happening 70%, which is 0.7, then the probability of event not happening is 1 minus 0.7, which is 0.3. So next we will try to do a program in Python, and I would like you to have a program that will simulate flipping a coin, count head, in 100 random tosses of a coin. We'll try to do a little experiment of generating random data. First, we include all the libraries, pandas, seaborn, numpy, matplotlib. Right. Now we make the coin toss. Make a random coin toss it 100 times, count the heads or tails. So maybe I will create variable number of tosses, so I can easily change what will be the number of tosses. Is np.random random choice function, and this random choice will make a bunch of random numbers. Well, I have to tell it what to choose from, so maybe a head, tail. Right, so it chooses head or tail randomly. I can say how many times it should do the choice and tosses. Now I have a long array of heads or tails, and if you want, you can also say what is the chance that head and tail is selected. Here I'm saying head is selected with 60%, tail with 40%. So there should be more head than tails. Right? This is doing unfair coin. Right. Now we create a data frame. Maybe I started with data frame pandas, and I can make a dictionary that says outcome is, well, I have to maybe give this a name, coin outcomes, and hope. So let's see it. So now there is a data frame, outcome, right, and now I can try to plot it as an S, or maybe missing parentheses, seaborn I called, and then count plot. Yeah. Too many parentheses. Right, it didn't do anything. It created the plot, but not much in it. So I need to say that what are we trying to plot. So I will say data is the data frame. I should give it a name here. And what is on the x-axis is the outcome. And here it is. Heads a little bit more than 60, tails a little bit less than 40, so almost 60 to 40. Right. Now it's closer to 60 to 40. Now it's switched that tails are first and heads are second. Right, so it's kind of around it. It's not exactly 60 and 40. A little bonus if you want to distinguish head and tail by color, you can write here hue equals and the name of the column, and now the head and tail are also distinguished by color. Here is an example to practice the definitions. Here a box that contains 3 blue balls and 4 red balls, and the question is, if we randomly pick a ball, what's the chance it is a blue? Right? It will be relatively easy to have a guess that it's 3/7. You have 3 blue balls and total 7 balls, so if you pick randomly one, hopefully it's 3/7. Well, let's see. What is the experiment? Experiment here is picking the ball. What's the outcome? Outcome is that we have one of the 7 balls. Right? And what's the sample space? The sample space is one of the 7 balls, all of them with equal probabilities. Right? And what is the event? The event is that the ball is blue. You could think of it that you have 7 different balls, 1, 2, 3, 4, 5, 6, 7, where the balls 1, 2, and 3 are the blue ones and the remaining are the red ones. So what you could think of is that there is an event that you want to select the ball with number 1, 2, or 3, which will be the blue ones, and then the probability of the event is 3/7, because there are 3 outcomes that satisfy the event out of 7 outcomes total. If we run the experiment 70 times, here are the outcomes that you can have. Right? On the left, you see what would you expect. If you have 70 times the experiment, then 30 times you would get a blue ball and 40 times you would get a red ball. Funny thing that the colors are kind of flipped in these pictures. That's what happens at the, let's say, idealized expectation. On the right is what can also happen. Right? It can happen that there are way less than 30 blue balls, or that it can happen that the number of blue and red balls is almost the same. Right? It's one thing that one has to keep in mind, and people usually get wrong, is that if there is something that has a chance 3/7 and you do it many times, it doesn't mean that you get exactly 3/7 ratio. It can be quite different. Right? As you have more and more experiments, then this goes closer to 0, the ratio, but the difference of the ratio from the expectation, but it can be different. Trying to do balls from a box is very similar to do the coins tosses. Right, so maybe I'll start and pick how many experiments are we running. We are running this thing 100 times. Now I'll random choice. So we have the function that will create the choice. We have blue balls or red balls, blue, red, because it's red ball. Size is the number of picks. Bam, I have the long array, and now I have to do the simulating that 3 of the 7 balls are blue and 4 of the 7 balls are red. So now it is looking like the 3 over 7 for blue and 4 over 7 for red. Okay. And you should use Seaborn to visualize. So here is balls outcomes. Save it into a variable and make a data frame. df balls and do the dictionary where I write the name of the column. Now the data balls outcome. Alright, df balls, I want to this be the name, and pd dot data frame df balls. I'll let it print. Right, what did I mess up? Balls outcomes out now. Alright, good. Now I have the data frame. Is the outcomes in it of the random experiment. So I'll try to plot it. SNS count plot, and on the x-axis I have the column outcomes. Data is the data frame. Okay. We had some is blue red. We can do the here order, and if you say order and you specify it in some way, then red will always be the thing on the left, the blue will be the first one and red will be the second one, right? So here number of red and blue is almost the same. You can also say hue outcome. Does it say hue entries doesn't appear. Outcomes, right? So now we are lucky the first one was blue as blue and red as red, right? So and now you can see the blue has the probability that is what 3 over 7 and red has 4 over 7. So despite the red having bigger probability, it happens less often than blue, at least in this particular experiment. So you should be keeping that in mind, that probability is not a guarantee. Let's try a more entertaining example. So I have still the same bin, these balls, 3 blue, 4 red. And now the question is, what's the probability that we will draw a blue ball first and then we draw a red ball? Means that you pick 2 things from the bin. First you pick a ball, then you pick a second ball and ask what's the chance that the first one was blue and the second was red. Right? Here it is more useful to say what is experiment, outcome, sample space and event. If you do this, then it will be easier to calculate what's the probability of the event. Right, so let's see. Experiment, it's the taking one ball and then another one, right? So what's the outcome? Outcome is a pair of balls. Here it really helps to have the balls numbered 1, 2, 3, 4, 5, 6, 7 with maybe the feature that 1, 2, 3 is blue and 4, 5, 6, 7 is red, right? So I will pick 2 balls. For the first one I have 7 choices and for the second one I have 6 choices because the first one was already picked, right? So 6 times 7, 42. So I have 42 is the number of possible outcomes in the sample space, and the outcomes are pairs of balls, and how many of them are good, right? The number of pairs that are good is for the first ball it must be one of the 3 that are blue, and for the second one it must be one of the 4 that are red. So it is 3 times 4. So 3 times 4 are the good outcomes. This corresponds to the event that the first one is blue and the second one is red. Right? And now we know what's the probability of the event because we know how many outcomes are good, which is 12. We know what's the size of the sample space, 42. So the probability is 12 over 42. The multiplication rule is a way how you could have solved the previous example as well. So let's look at it. I have 2 events, A and B, and I want to know what's the chance that both happen. The event A would be the first ball is blue, and event B could be that the second ball is red. Okay? And here I want to know what's the chance that both happen at the same time. And this can be done by first calculating that one of them happens, P of A happens, times the chance that the second happen, subject to we already know the first one happened. It's written just by P of A times P of B, and then you have the horizontal line A, which means chance of B subject to A happened already. Right? So in the example, the chance that A happens, which is the first ball is blue, is 3 over 7. That's easy to calculate. And now the P of B subject to A. If B is the event, second ball is red, and I know the first ball is blue, then I still have 4 red balls and only 6 left, so it would be 4 over 6. So 3 over 7 times 4 over 6, which is 12 over 42, same as in the previous example. The answer, if you use the multiplication rule, is always less or equal than each of the 2 chances of events A and events B, right? Because you are multiplying 2 probabilities, and that's always a number between 0 and 1, so it has to be less or equal than each of those. And there is a, you can think of it that if you have more and more events and you want to have them all happen at the same time, what you are looking for are outcomes that are in the intersection of all of them, and possibly the number of outcomes is decreasing as the number of events that you want to satisfy at the same time is increasing. So that's why the probability is decreasing when if you ask for several times at the same time. Addition rule is a rule that will help you make complicated event as sum of probabilities of simple events. Right? So here is write up. If you have A as event that can happen in exactly 2 different ways, then chance of event A happening is the chance it happened in the first way, or chance it happened in the second way. So maybe we should have an example. So here is example. So event A is that on the dice you roll 2 or 4. Okay? And the event happens that you either roll 2 or you roll 4. So what you can say that the probability that the event A happens is the probability that you roll 2 plus the probability that you roll 4. So probability of you roll 2 is 1/6, probability you roll 4 is 1/6, so 1/6 plus 1/6, 2 over 6. Okay? And the answer, what's the probability of event A, is always greater or equal than each of the two probabilities how it can happen in the first way and in the second way, but still always at most 1. Here is a third example. Let's see. I have still the box that has 3 blue and 4 red balls. What's the probability that we will draw 1 red ball and then the second ball is of the different color than the first one? Right? So now it's a little bit tricky. So first you pick a ball and then you try to figure out that the second ball is of a different color. So here we can use the addition rule nicely, right? So what are the possible events that will satisfy this event? So first you have the ball blue and then second is red, or first is red and second is blue. So you can say that the event, the 2 balls have different color, can be decomposed into 2 easier events, and only one of them can happen. Right? They cannot happen both at the same time. That's important if you want to use the addition rule. So first blue and second red, or first red and second blue. And you calculate these 2 probabilities separately and then sum them up. Right? And what's the chance that first blue and second red? We can use the product rule. First blue is chance 3/7 and second red subject to, now we know the first one was blue, is 4/6. And now the chance of first red is 4/7 and second blue subject to, we already know that the first one is red. There are 3 options for the blue out of 6 because one was already picked. So this is how you can calculate it, right? And together you get twice 12/42, so together 24/42. Is a complement is a nice way how you can make a complicated event into a simple event. Right? Let's say we have 4 coin tosses. I'll do an example. So you have head, tail, and you have 4 of these. Right? You can think of it as you have a string of length 4, and the letters that you are using are H or T. Right? So how many possible samples are there? Was the sample space? So you have these strings of length 4, which each of them has H on T. So there are 2 options for the first toss, 2 for the second, 2 for the third, 2 for the 4. So it's 2 to the 4. So together you have 16 different possibilities. Right. And now at least one head. If you want to enumerate those that there is at least one head, you have to say, okay, so the outcome was maybe that they were all heads. Okay. Or first 3 tosses were head and then tail. Or 2 tosses head, then tail, and then another head. And what you would have to do is enumerate all of them. And it's kind of annoying because there are many of them. So instead of calculating the probability that there is at least one head, you can calculate the probability that there is no head. Having no head at all is much easier because there is only one outcome that has no head at all. Right? It's the tail, 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 tail. So calculating the chance of no head is easy. It's 1/16, and then at least one head is 1 minus the no head because it's the sample space is the complement, right? So this shows how the complement makes calculation a little bit easier sometimes. Okay, so here is some ideas about problem solving. Right? What what should you do if you want to calculate some probability? You know? If there is several things happening, then good start is to see what has to happen first. What happens on the first try? Right? If you know what thing should be happening on the first trial, then maybe multiplication rule would be a good idea. Because in the multiplication rule, you calculate what happens on the first trial, and then you calculate the probabilities of the remaining trials, subject to what happened on the first trial. Okay? If there is no clear answer, like that it can be several different things that can happen on the first trial, then maybe you can list the distinct ways and use the addition rule. So you partition the sample space into different parts, and they are distinguished by what happens on the first trial. Or if the list is long from the above type and complicated, maybe the complement will do it. Like we had the complement for counting the chance of having at least one head. Okay? So these are suggestions. Right. Let's say that you have a group of 100 people, and they include Alice and Bob. Okay? And from this group, we randomly select two people. We say, you are the first person, you are the second person. Right. So what's the chance that both Alice and Bob are in the sample? Which means that they are both selected. Right? So what's the number of outcomes that satisfy the event that Alice and Bob are selected? You can say it's 2, because either first is Alice and then is Bob, or first is Bob and then is Alice. And what's the sample space size? For the first person, we have 100 choices. For the second person, 99 choices. So it's 2 over 99 times 100. Another question? What's the chance that neither Alice nor Bob are in the sample? The sample space is still the same. So its size is 100 times 99. And how about not being in the sample? So first we have to say who's the first person. And for the first person, there are 98 choices. Right? 98, because it cannot be Alice and Bob. And for the second person, there are 97 choices, because the second person cannot be Alice, cannot be Bob, and cannot be the person that was selected first. Right? So this is a little entertainment. Birthday problem is this paradox that if you have a group of people, it doesn't have to be too big for two people have the same birthday. So if you have some time, try to see how large group of people do you need, such that there is a more than 50% chance that two have the same birthday. Right? You can try to assume that they have 365 days in a year, and there are no twins. The birthday day uniformly distributed over the whole of it. Let's try to simulate the birthday problem. Called the birthday problem was saying that I would like to know how many people I need to have such that the two of them have birthday at the same day. Alright, so I have K is the number of people, suggestion, right? Maybe 22, 23, okay, I'll do 22. Right, now I'll try to generate birthdays. So how do we do it? NP random, and we can write and int from 1 to 365, right? We have random integer, which is the day of the year, except the leap year. Okay, and then I want k of them, so now I have k different days. Right, I would like to know, so maybe I will call this the birthday. Right, I would like to know if there are any duplicates in here. Right, so, simple way how to make the test is the following. I will try to calculate what is the number of birthdays, right? And it's always 22. And what if I make a set out of the birthdays and then calculate the number of different ones? So now it's 21, which means there are two people that have birthday on the same day. So if the set of birthdays, which combines the entries that are the same, is less than k, then two people have the same birthday. I would like to repeat the experiment 100 times. For that, and count how many of them are. Let's see. Match count is 0, and if they have the birthday at the same time, I will do match count. I increase it by 1, and now I will run the whole thing 100 times. So maybe I will create a variable num experiments, how many experiments I want to do, and now for dummy variable in range num experiments. So now how many times? I'll do it 100 times. I don't really care about the number, so people have the same birthday. Print match count. Let's see. So 96 out of 101. This is very suspicious. As the number should not be more than 100. Alright, maybe I need to have the same number. Match count 43, 44, 43, 42, and 57, 56. Right. So that's how many times there were two people with the same birthday out of 100. We can also divide this by number of experiments, and now we get a number that if you are getting around 0.5, then it's about half. Right? If I have fewer people, 10 people, then the chance is kind of small that there are two of them that have the same birthday, or at least the experiment. Okay? It seems still kind of small. Even at 18, we cannot get to half. When we get to 22, we sometimes get the half or a little bit more. To 23. If you have something bigger, like 33, suddenly it jumps. Okay? So about 22, 23 is the threshold for how many people do you need in the group to have a chance over 50% that two of them have the birthday on the same day. Another problem is this Monty Hall problem. So here's how it goes. There are 3 doors, and you don't know what is where. They randomly mix things that are behind the doors. One of the doors has a car behind, and the 2 other doors have goats. And here is how it goes. First, you pick a goat. You pick a door. You are trying to get a car, right? And hoping that there is a car behind the door you pick. Then the host of the show opens the door that is not yours, and shows you that there is a goat behind the door. So now there are just 2 doors. One is the one you picked, and the other one is another door, right? And the third door now is eliminated. And you can change to the other door than you picked, or you can keep the door that you originally had, right? So the question is, should you change or should you keep the original door? Which one would you do? The answer to the game is that you should change, right? If you keep the door you stayed with, then you had 1/3 of chance to getting the car, right? 3 doors, 1/3 chance. And the thing that you saw a goat or not saw a goat doesn't change the outcome, right? Because originally you had 1/3 chance of getting the right spot, and then either you got it or not, right? But if you change, the game is different. So to do it, what we'll try to do is say that we always pick the door 1 and try to see where are the possible locations of the car and what are the chances that we get the car, right? So here are the possible choices. So here are the possible options. So either the car is in the door 3, or it is in door 2, or it is in door 1. Okay? So if the car is in door 3, now we'll look at the first line in the table. We chose a goat that was in the first door. Then the host of the show reveals goat, it is in the second door, and if we change the door from first to third, we get the car. Now, if the car was behind the door number 2 and we picked door number 1, then the host of the show will open door number 3, and if we change from number 1 to number 2, we do get a car. And the last option is that the car was behind the door number 1 and the other 2 doors were goat. The host opens one of them, for example, the second door, we switch to the third door and we get a goat. But what is the chance that we got a car? In 2 out of the 3 runs, we got the car. So now the chance of getting car is 2/3. But before, chance of getting car was 1/3. So this is a example how probability or understanding can change your fortunes. So the suggestion is, in this game you should always change, because suddenly your odds will go from 1/3 to 2/3. Here, try to do a following experiment. We have 2 players, A and B, and they each have 1 dice. They both roll, so there are 2 dice they throw. Player A wins if the maximum is 1, 2, 3, or 4 of the 2 dice. The player B wins if the maximum of the 2 dice is 5 or 6. The question for you is, who would you rather be? Would you rather be the player A that wins if the maximum is 1, 2, or 3? Or would you rather be the player B that wins if the maximum is 5 or 6? Try to see what's the sample space and what are the events where A wins, where B wins, and that should reveal the answer. You can also try to Google the YouTube video that shows this. It's kind of entertaining. Right, let's try to play the game 100 times and see if A or B is winning more often. Will give us some guess. Right? It's not the mathematical proof, but it's entertainment, experimental thing. So I will try to do number of experiments, 100, and wins for A. It will start at 0 and then I will try to count. Alright, so how does the experiment work? So I have first die that will be random int it is between 1 and 7, the first one, and then the second one. I can try to print die 1, die 2. It's okay, I am rolling 2 dice. Now I would like to know what the max is. Max of the 2 is max die 1 and die 2, right? I can try to print the max roll. Okay, so I have max, and now if max roll is less or equal than 4, then wins for A. I add 1 to them. Alright, so what's the percentage? Percentage A1, it is wins of A divided by number of experiments times 100. Here I am dividing by 100 and multiplying by 100. So just the wins of A is the right thing. Okay, number of experiments, I'm still doing only 1 experiment, so for nothing in range num experiments, if I select the whole block and press tab, it indents it. Right. A 1% of the games. Alright, so here A1 41%, 43%, 34, 46. Right, so if you keep doing it, it looks like most of the time B wins. So being B is the better thing. You can increase the number of games and you will be getting number that is closer to the real one. Because this is not concentrated. Yeah. But that's good enough that we are kind of sure that it's better to play as B if you want to play. Right. I'll try to write another way how you can do this thing. Maybe decrease the number of experiments so it runs faster in more Python way, and that is we will try to create a list of outcomes. So I will do this outcomes. Maybe I'll give it a name in the end. So I will have A, and now I will do it and we get A if max of and list that has 2 random numbers at least 4. And I will do it for underscore in range num experiments. Maybe I should. Okay. And we are missing the else b. So we will say it like this. Here we have a for loop that that creates the list. Okay. So, and in the list I will say a if the maximum of the 2 is at most 4, should be. Of the 2 dice at most 4, otherwise it has b. So now it's a list that says a, b, a, b, a, b. Whoever won is written down here as a or b, right? And now I will write this as outcomes. You'll remember this. And outcomes count a okay, now it counts how many times a is appearing in the list. Okay, and that's good enough, because now I can write percentage a1 is wins for a, which is the outcomes come, divided by number of experiments over 100. But maybe I can just write divided by len of count. Okay. And we probably will not get the same number because we are running the same experiment twice, but we get similar ones. Now if you have it this nicely as a list, you can put it into a data frame, pd.data frame, and you say this is determining who the winner is, name of the column, column, and outcomes. So create a dictionary. Now I have my data frame that is saying who won, and now I can plot it, SNS, count, plot, data. This data frame, I have to say what the x-axis is, axis winner, and here it may be useful if there is a first and b second always. So seeing it in the plot, a is on the left, b is on the right, so b is winning in most of the runs that we are trying. Okay? Try to show the rest of this line again, how I did it in one line. This is also okay.